not only for QCD meets gravity, but also many other things that we have been hearing and we'll hear more in this workshop. And one thing that cannot be emphasized too much is that the scattering amplitudes indeed reveal a lot of structures in quantum field theory. And for today's talk, we'll be mostly focused on one of the most remarkable quantum field theory, which is n = 4 super mu's in the planar limit, for which we actually have like these three related phases of studying scattering amplitudes. One is that we have this all loop integrants, where we've been keep studying using generalized unitarity, also discovering new geometric structures such as positive geometry and the amplitude hedron. The second side is this integrability structure that we've seen in the planar limit that allow us to, in principle, compute amplitudes at any coupling related to ADS-C if there's strong coupling and so on. And then most of my talk today will be focusing on the third thing, which is, of course, the amplitude itself. After we do the loop integrals, we get this transcendental functions at each loop order, and closely related to them are the Feynman integrals that add up to the amplitudes. And of course, there are a lot of things that I don't have time to go through, like the bootstrap for hexagon, heptagon, and so on, the symbology, the cluster algebra structure, and many ways of computing Feynman integrals and so on. So the starting point of my talk today will be the remarkable duality between amplitudes and the Wilson loop in this theory. So we all know that both as strong and weak coupling, it's been more than 10 years that we've learned that the first that MHV amplitude, after you strip off the key level prefactor, is dual to a light-like polygonal Wilson loop in this dual space. This has been generalized to roughly 10 years ago, generalized to super amplitude and dual to the super Wilson loop, where you not only have the connection for gauge fields, but also you can add fermions and scalars and so on in this super dual space. So the super Wilson loop is defined in the dual space, which has an n = 4 SUSY extension, that the cusp of the Wilson loop is related to the the edges of the Wilson loops are light-like in this equation, you can see. So the difference of two adjacent cusps are given by lambda tilde. And then there's also the theta supersymmetric extension, the fermionic component related to the lambda eta. And just the amplitudes have IR divergences, which are directly related to the UV divergence of a Wilson loop to all loop order. And this picture tells us something very important about both objects. The amplitude enjoy a superconformal symmetry, while the Wilson loop tells us something. There's a superconformal symmetry living in the dual space, which we call dual superconformal symmetry. It's also discovered at the same time. And the remarkable thing is that when you put them together, they actually generate an infinite dimensional Youngian symmetry, which encode the integrability of the theory. So here are some examples of this generator of the symmetry. You can see that the usual conformal symmetry and the dual one using the usual spinor variable. And we all know that although at tree level we can realize this, we can see the amplitudes are Youngian invariant, but starting loop level, these symmetries are actually broken by the divergence. And the only Youngian invariants to all loop order are computed by loop amplitudes as some compact contour. These are the so-called leading singularities, and they can be computed from this mathematical construction of positive Grassmannian and so on. And the actual loop amplitude, which we compute at the actual loop contour, they must have some anomaly, right? They must have some anomaly for the symmetry. So just for the dual conformal symmetry, there's the first anomaly equation proposed by German and collaborators, which tells us how to restore, in some sense, restore this symmetry. So in order to really restore the symmetry, we need to subtract the IR divergence, and this can be done by the BDS ansatz, which is the exponential, essentially the exponential of the one loop amplitude. And once we normalize the amplitude by defining this BDS normalized amplitudes for n point and nk MHV, we have a very nice object. This is a finite object to all loop order, and it's dual conformal invariant. So it's a function of 3n minus 15, where 15 is the dimension of this dual conformal group. So many cross ratios, and it is invariant under chiral half of the dual supersymmetry, but interestingly, it's not invariant under the other half. And this finite loop amplitude can be written as the simple Youngian invariance, which encode the SUSY and is always rational algebraic, times the non-trivial part of the all loop amplitude, which are this transcendental function. At L loop, it's believed to be some transcendental function of uniform weight 2L. And especially in the simplest sector for MHV and next MHV, they are believed to be just given by generalized polylogs, so control of polylogs, which are defined as these iterated integrals. And this led to the study of all this transcendental function using the tool of symbol, and you can study what kind of letters, which means these singularities of this transcendental function appear in the answer. So for 6 and 7 particles, there's a remarkable conjecture that the whole alphabet of these symbol letters are given by the cluster variables of G4n, which are where the momentum, where the kinematics lives. So for 6 and 7 particle, the whole alphabet consists of only 9 and 42 letters, and using this and some other constraints, we can bootstrap these amplitudes up to very impressive high loop orders. Okay, so
Hi Son.
Yeah.
Sorry to interrupt, but you know we did it in our 2013 paper, right?
Sorry?
The cluster variable observation was in our 2013 paper.
Yeah, sorry.
Not in the work that you cite, right?
Right. No, I mean, I'm talking to the 7 loop results. Sorry. Yeah.
But
course.
6 and 7 we observed that in our 2013 paper with Sasha.
Yes, of course.
Yeah.
Yes.
Thank you.
It's yeah. Thank you.
Yeah. Thank you.
So let me just briefly introduce the kinematics I'm talking about. So I'll be using these momentum twisters, which are some the variables introduced by Andrew Hodges. You can view them as these light rays in this dual space. So they allow us to realize the dual symmetry, including the fermionic part, defined in this way. And when you see this 4 bracket, they mean the very basic SL4 invariance of this kinematics. And in this variables, all the dual symmetry become very nice. So the dual conformal symmetry and the half of the supersymmetry, they all directly annihilate the BDS subtracted amplitude, but not the other chiral half. So this Q bar is not this Q bar do not annihilate the BDS subtract amplitude. And also the usual superconformal symmetry become level 1. So we need to study the anomaly of Q bar and at least one level 1 generator in order to determine how amplitude behave under this symmetry. So this is the so-called Youngian anomaly equation that consists of the Q bar equation and its parity conjugate that give you a level 1 equation. So the Q bar equation is an equation that tells you the right-hand side of this symmetry is given by some collinear integral, where you can imagine that you insert additional fermion along edges of this Wilson loop, which I think the thing I want to emphasize is that this insertion has this form that you take epsilon to 0 that give you the collinear limit, and this tau describe the position where the insertion is at. And this is a very nice equation. It in principle determines, I mean, this together with this parity conjugate in principle tells you how to make the symmetry of the S matrix completely exact. So if you move this anomaly to the left-hand side, you can view them as the quantum corrections for the symmetry. So that makes you write down the exact symmetry for the whole S matrix. Okay, so just using these equations, I mean, these equations, the Q bar equation and this conjugate are first order differential equation that can determine the whole S matrix. So up to some simple Yangian invariant, which you can fix by collinear limit, all loop S matrix, or even non-perturbatively, in principle, they are determined by these differential equations. So in practice, what we've been used to so far is only the Q bar part. So the Q bar part alone can tell us how to compute MHV and next MHV amplitudes. Once we know the lower loop amplitudes on the right hand side, so we can use the lower loop but higher K amplitudes on the right hand side and compute the right hand side and then solve this differential equation to compute MHV and next MHV. The reason is that for MHV and next MHV, there's no kernel when we replace this Q bar differential operator by the total differential operator. So for MHV is of course trivial because it has no dependence in chi, but in the fermionic part, but also for next MHV, there's no non-trivial kernel. So in the final result is like the following. So if you use the Q bar equation, you can determine for MHV and next MHV, the total differential of the amplitude is given by some last entry, where the last entry for next MHV also means how last entry of the symbol is paired with the Yangian invariant, times some collinear integral, times some this tau integral of lower loop amplitude. So this is how the structure works. So using this, you can first determine to all loop order what are the last entries, which has been very useful for the bootstrap. This is important input for the bootstrap. But also you can use it if you give me the lower loop amplitude, you can use it to compute the 2 or 3 loop amplitude directly. And here the most important step of the computation is you do this so-called 2/3 integral, where the /3 part is just a fermionic integral that give you, for example, the last entry of MHV is like that, and then you do the residue computation of extracting the epsilon to 0 limit, and then finally you do this tau integral that give you the how you see the lower loop amplitude give you the total derivative of the higher loop amplitude. So in this way, for example, you can trivially compute all the 2 loop endpoint MHV amplitude. Okay, and you can also do it, for example, for 2 loop next MHV 7 point, which will in turn give you 3 loop 6 point. All this has been done like 10 years ago, and it gives you all loop prediction for MHV amplitude, for the last entry of MHV amplitude, but also for the last entry of the next MHV amplitude as we recently classified. Once you know the R invariant, Yangian invariant for n square MHV, you can just do this. But a new problem arises when you compute 2 loop 8 point next MHV, because now you see some square roots appearing. So nobody knows really what are this what are the possible letters involving square roots, and because the cluster becomes infinity, what is the complete alphabet? So this is what we did last year by considering the collinear integral of this 1 loop n square MHV amplitude, which involve this 4 mass boxes that has square roots in it, right? So here I want to emphasize one thing. So when you do this tau integral of this 4 mass box, naively, this doesn't look like a pure integral, because in front of this 4 mass box, there's some Jacobian, there's some prefactor that involve this square root. So it not only makes the integration difficult, but it actually makes it look that is not going to be pure integral. But actually, there's a very, very simple change of variable that solves both problems. So for example, if you take this variable tau to just the z of tau, which is the square root appearing in 4 mass box, you can convince yourself that the tau integral of your 4 mass box just look like this. So the prefactor just go away, go into this d log of the z, and then you can just compute it, and the weight 3 result you get looks very nice. It looks like the symbol of 4 mass box times some so-called algebraic ladder, which are something new, something that involves square root that start to appear at 2 loop. Okay, so this is the key step.
5 minutes left.
Yes. Okay. So this is actually the key step that give us the 2 loop next image V result, at least the part that involves square roots. So just because we can do this rationalization, we get a very beautiful result for the part that involve algebraic letters for any number of points at 2 loop next image V. So this is the part that looks like 4 math box times some algebraic letter. And then the final entry and R invariant, which are all rational, are correlated with what algebraic letter that appear here. And you can count how many there are. They always take this form. And for 8 points, the simplest case, there are 18 of them. But also for any number of points, we find that for each square root, there are, in the most generic case, there are 17 such independent algebraic letters. And I want to also say something that when you compute a very special class of component of next image V, it actually becomes free of the square roots. So this is, although the whole amplitude, next image V amplitude contains square roots, if you take this component, it's given by the difference of these 2 double pentagon. And that is free of square root, as you can see from the Q-bar calculation. But still, there's this long-standing problem of how to compute individual double pentagon. So I think after this integral has been written down for 10 years, nobody has been able to compute it beyond 7 points. So the most closest people have done is last year when Jake and friends computed the double pentagon at a particular numerical point for 8 points. So the next we'll use something very similar to the Q-bar equation I described just now to compute the most generic double pentagon, which happens at 12 points and above. Okay, so let me switch gear and in the last few minutes tell you how to use something very similar to Q-bar, also from Wilson loop, to compute just individual Feynman integrals. And this is not surprising that Wilson loop are important are very powerful also for computing Feynman integrals, as Simon already did when he computed the differential of 2 loop MHV. This Wilson loop diagrams give you very nice results for the multi-loop integral. And we can see that the component of next to MHV endpoint is also just given by 2 Wilson loop diagram, which each of them is just a double pentagon. So each double pentagon looks like a Wilson loop diagram. And why is it useful is because I can now, once I write it as Wilson loop diagram, I can actually relatively easily perform this loop integral and left with this integral along the edges of the Wilson loop. And this is, of course, in simple cases, this is well known. For example, this is in this toy model of chiral pentagon. You can see this is also given by a Wilson loop diagram, and I can perform the loop integral using this star triangle identity. This is a very simple identity that tells me that for the fermionic propagator that has this square double propagator here, I can do the loop integral, and I'm left with this very simple 2-dimension line integral or edge integral here. And it can even be written very nicely as 2 d-logs. So here you can see that the a single pentagon is written as this 2 d-log integrated along the 2 edge I and J. I mean, of course, the answer to this is very well known, some dialogues, but this representation makes it completely manifest, even trivial to do the dialogue integral. And the geometric meaning is really you take some canonical form of a curvy triangle and integrate it along another triangle. That's just it. And now we can do double pentagon in basically the same way. So you apply the trick to one of the 2 pentagons, and you find that the double pentagon is given by a 2-dimensional integral of an interesting hexagon. The hexagon now depends on this insertion x and y I introduced. So in principle, you can actually do it as 4-4 line integral, but that makes it look more complicated. So we use this mixed method that the 2 loop integral now look like a 2-dimensional integral of a 1 loop integral that you can easily write down. So this 1 loop integral is now some box integral times some 2-form leading singularity that you need to integrate. So in principle, at this, basically at this step, you are done, except you still need to deal with the same problem as the 4 math box as I mentioned. So now you have some rationalization to do. So proceeding exactly as before, you can write the whole thing as in the new variable as some d log integral of dialogues, and then you end up with the weight 3 after you do the first tau integral. And at this stage, you can already see how the when you take the difference of the two double pentagon, ijkl and the jkli, all the square roots cancel, because this whole part that involves square roots is look quite simple. So this is my last slide. Now you can do it for the last tau integral, and you obtain some weight 4, and you see that quite non-trivially, the last entry is completely free of square roots. So all the square roots appear in the third entry. The final result is looking like some 4 mass box times this third entry that has square root, and then the last entry is again very simple. So not only that the next image V component is free of square root, if you take the cyclic combination of these guys, you see this is the first time one can really compute the 2-loop endpoint MHV just from Feynman integral. So you can really just sum it over all this double pentagon to get MHV. At least for this algebraic part I show you, you see why MHV amplitude at 2-loop is free of square root. Okay, individual integrals have square root, but they all cancel in this cyclic sum. So basically, I just give you a very quick tour of how Wilson loop are powerful, not only for computing the full amplitude, but also for Feynman integrals through the Q-bar equations. Obviously, the next step will compute the 3-loop MHV from 2-loop next MHV. But also, it'd be very interesting to explore more the structure of these integrals and the amplitudes, especially what are the geometric meaning for this Wilson loop representation. Okay, I'll stop. Thank you.
Okay. Thank you very much. There's a bit of time for questions, so if you know how to raise your hand, you can do it. Otherwise, you can just go ahead. Enrico?
Hey, Song, that was pretty impressive. Can I ask you a question? It might be a little technical, but when you get this twofold integral over this chiral hexagon with the measure, so then you say, well, that hexagon has multiple of these 4 mass boxes inside of it. So once you rationalize, do you rationalize everything together, or do you take it apart in this box decomposition and then rationalize each term, each integral individually, and then put them back together at the end?
Right. We have to rationalize one by one. So there are 4 of them, and but the rationalization is just in each of them you change to the z of that 4 mass box. So it's pretty straightforward. They're actually relabeling of each other.
Yeah. Okay. So you have no global rationalization.
We have no global rationalization. Yeah.
Okay. Great. Thanks.
Maybe just a quick question on my side then. You mentioned in your last slide non-perturbative S matrix. Do you have anything?
Right.
What do you have in mind?
So what I mean is that just in principle, we can just define the question of, so we've always been want to ask what is the question to which the answer is the S matrix, right? But at a non-perturbative level, in principle, you could just say the question to ask is something that satisfies both Q bar and its parity conjugate. So if you can make this statement very sharp, then I think that's going to be something very useful, because for now we are only using this this quick Q bar equation and its parity conjugate to, actually we haven't really used its parity conjugate, but we're using it for perturbative calculation. But there's evidence that both these equations work at non-perturbative level. So how to put it in use and use that as basically as a starting point of finding some non-perturbative structure would be the, I think, one of the most important questions along this direction.
Yeah, okay, cool, thanks. Okay.